So we started talking about the electrical potential. We introduced a new scalar field called the electrical potential. Electrical potential. And the idea is that from the two postulates of electrostatics, so we have Gauss's law, divergence of E. Remember, divergence is the way a vector field compresses or converges or diverges, compresses and expands. That's related to the charge density over epsilon naught. This is in differential form, and then in global form, local form. So we have always local or infinitesimal form, meaning you zoom in into a really small region of space, and then global form or integral form, where you zoom out and sum over a large region of space. So this is called differential, and this is called integral. And it looks like something like this. We integrate over a closed surface of E dot ds equals Q enclosed over epsilon naught. This is Gauss's law. And then we have the circulation law, which is the curl. What happened? Oh, which is the curl of E is 0. Which is in integral form is simply that if I go through a curve, closed curve, circulation, so this is curve C, or L, let's call it L, circulation of E dot dl is 0. Now, one of the null identities, if you remember from the null identity, one of the null identities says that if I have some vector field, some A, right? If A such that the curl of A is 0, then we can write A as the divergence, not the divergence, the gradient of some scalar field. And by convention, we said we use the minus sign here, right? And that comes from the null identity that the curl of a gradient of some scalar field is 0, right? So this is one of the null identities that we proved in vector calculus. So in electrostatics, the curl of E is 0. So this tells me that E can be written as the gradient of some, because E is in electrostatic is irrotational, right? It does not rotate around any axis. It has no current sources. If there was a current source in electrostatics, it would be a magnetic current, meaning a current of magnetic charges. But magnetic charges don't exist in nature, right? So there are only electrical charges. So because the curl of E is 0, that means we can write E as a divergence of some other scalar field. And this scalar field we call the voltage or the potential, electrical potential. Essentially, what the statement is saying is that in space you can define the electrical field by a vector field, an arrow at each point in space. A quantity has a magnitude and a direction, right? That's what a vector field is. But what in electrostatics, this is too much information. This is not the most concise way of describing the field. You don't need to describe the electrical field as a vector field. You can describe it as a simple scalar field. And this is nice because in many ways, like a scalar field is simpler to deal with than a vector field. A vector field, you have at every point in space, you have to worry about a magnitude and a direction. With a scalar field, at every point in space, you only have to worry about a magnitude at every point in space. There is no direction anymore. How do you get the electrical field from the scalar fields? You find the gradient of it. You do the gradient operation and you get back the electrical field. Because the electrical field is a representative of the electrical force. If you want to find out what the force is on a charge, you need to know the electrical field, right? So that you can multiply that charge by so you can get QE, which gives you the force. So this scalar field is called the voltage, and it's a new field, right? We can give it its own unit. So we can give the unit of volt for this field. So at each point, we say like at this point it's 5 volts. At this point, it's 6 volts, right? But we need to interpret physically what does this unit mean. Okay, so the integral of E. So let's take the integral of E from, let's say you have a space, you integrate E from point 1, P1 to P2. Okay, so the integral of E dot dl, now we know that I can write E as this, right? So I can write this as minus integral P1 to P2 minus gradient V dot dl. I can take the minus out. This becomes integral from P1 to P2 gradient V dot dl. And remember from the fundamental theorem of calculus, I can write this. This is integral differentiation operator under the integral. I can write this in terms of the boundary. So this becomes VP2 minus VP1. Okay, so interesting thing. So the right. So this is what right. So yeah, we go from P1 to P2. So P1 is the start point, P2 is the end point. Instead of E, I put minus gradient V. Why did I put a minus here? That's weird. There is no minus here. I don't know why I put a minus here. Okay, and then the minus goes out here. So there's still a minus here. There's still a minus here. Okay, and then there is a minus here. Okay, now what I want to do now, I want to multiply. I don't like this minus sign. I want to multiply everything by -1. So if I multiply everything by -1, right? So I took this E dot dl. I put in minus grad V. There is a pesky minus sign here. So I multiply everything by minus, and then I multiply this by minus. So this tells me that whatever the scalar field is, it has the property that VP2 minus VP1, the difference in the scalar field between 2 points, is just this integral, P1 to P2 E dot dl. It naturally comes. This has to naturally happen because of the way the gradient is defined. So what does this tell me about the units? So this has units of V, volts. What does it tell me about this? So those two sides have to be equal. What are the units here? The units here, we're integrating, we're summing up the electrical field, which is Newton over Coulomb, dot meter times meter. So that tells me that volt equals Newton dot meter over Coulomb, right? V is not a fundamental unit, it's a derived unit. It's a new unit that we introduced. But this is telling me a key thing about this unit. What does it represent physically? What is Newton time meter? If I have a force and I displace some distance, displace the system or the particle some distance along this force. So I have a force F, and then I displace some particle some distance D. F dot D is the work, right? Work is F dot D. Displacement times the force is work. So Newton times meter is work or energy. Work is energy. So really V is a representation of energy per unit charge. It's a method of measuring the energy in the electrical field. Okay? but yeah, so this is, and we'll show how to interpret this for a point charge. But essentially, with V, it does not with the voltage scalar field, it does not, with the really at the absolute value at every point, what does not matter. What matters is the difference between 2 points. And we see that because we're gonna follow now we're gonna follow the, what do you call it, assumption or the definition or the convention, kind of like potential energy. The convention for potential energy is for potential energy to be 0 at an infinite distance, right? You can take potential energy and add any constant to it, and it'll be the same. Everything will be the same. So I can take a voltage because E is really, you know, grad V. What if I take, instead of grad V, I take grad a gradient of V plus some constant K. V is the scalar field. V depends on position. This is same everywhere. Some constant that's the same number everywhere. Okay, this will be exactly equal to this, right? Because when you find the gradient of a constant field, it will be absolutely 0, right? So I can take, if I can take any voltage field and I can add a constant everywhere and everything will remain the same. So it is a convention to add a constant to the voltage field such that at infinity, such that V approaches 0 as distance x, y, z approach infinity, right? Or R in spherical coordinates approach infinity, right? Or in cylindrical coordinates, R and Z approach infinity. At a very large distance, essentially, we can add this constant, because if I have a scalar field V that represents E, adding any constant to it does not change anything, right? Because the gradient of that constant is going to be 0. So we add always a constant to it in such a way such that V at infinity is always going to approach 0 or going to be 0. So that's the convention. Okay. So that's it. That's the potential field. It represents energy. It represents, and I'm going to discuss exactly how does it represent energy from an intuitive perspective. But it's all mathematical. It's all from the property that the electrical field has no curl. Okay. So now the question: how do we calculate it? It is a scalar field, so hopefully it's simpler to calculate because we don't have to worry about calculating a vector at every point in space. We only have to worry about calculating a scalar. Well, we use superposition, right? We go back to the fundamental principle that if we can calculate something for a point charge, we can calculate the same thing for everything, right? Because of linearity and superposition. So remember, for a particle, for a charged particle with charge Q, and then this looks more like a G than Q. Okay, so if we center it in the coordinate system, we choose the coordinate system such that the particle is in the center, and we use spherical coordinates, right? We know that E is going to be R hat, Q over 4 pi epsilon naught, over R square, right? Where if I have this point P, this is E at P at a point, at a special point. So I have the position vector R, and R is just R magnitude, essentially. Okay, so this is Coulomb's law. But we're saying we can write this as minus gradient of some scalar, scalar field. Can we figure out what the scalar field would be? Could be, again, in the same spherical coordinates. Well, I'm going to tell you this field is from inspection. You can that's going to be Q over 4 pi epsilon naught R. And notice there is no more, this is no longer a vector, this is just a scalar quantity. Okay, so it only depends on the distance of the point from the origin. That's it. How do we show this? Well, we have to go back to the equation of the gradient. So you go back to your textbook or your notes and remember the equation of the gradient for a scalar field in spherical coordinates. It was delta U over delta R hat, plus 1 over R delta U over delta theta hat, plus 1 over sine theta du over d phi hat. Now, I by inspection, I assume that this is going to be this. Well, this is easy. dv. So what's gradient v? First, this term, the v does not depend on theta, so this goes away, dies instantly. V does not depend on phi, this dies instantly. What's left is du over dr. Right? So E is actually minus grad V. So this is E is going to be minus du over dV over dr r hat. I assume that V is going to be this. So it's going to be minus Q over 4 pi epsilon naught, and then 1 over R. What's the differentiation of 1 over R? It's R to the minus power minus 1. So it's going to be minus R minus 2. It's going to be minus 1 over R squared, right? And then there is this R hat here that shows up. So this equals Q over 4 pi epsilon naught R square R hat. We got back Coulomb's law, okay? So this is a good candidate for representing the scalar field or the potential field for a point charge. The question is that the only candidate? No, I could have added any constant here, plus C, and I would have gotten the same result, right? But the second thing we said is we want to add C such that we want to follow the convention that V approaches 0 as the distance goes to infinity. So do we have to here add some constant such that V approaches 0 as the distance goes to infinity? No, because this expression naturally approaches 0 as R goes to infinity, right? So it occurs naturally in this expression. Okay, so for a point charge, if we take the coordinate system centered at those charges, at that charge, the voltage is simply at every point in space is going to be Q over 4 pi epsilon naught over R. Much more simpler to calculate. What if the charge is not centered at the origin? Let's say the charge is centered at some call it R prime, and we're trying to find. So I use small or capital. Let me use capital. I mean, it doesn't matter. It's just a matter of what do you feel like at the moment. I think in the textbook they use capital sometimes and they use small sometimes. Let's see. Let me try to follow what they do. They use capital. Okay. So the position vector R prime to represent where the charge is. Remember, always use primed vectors or primed symbols for sources. And then the point where I'm interested in finding the potential has R. So in this case, V at P is just Q over 4 pi epsilon naught magnitude. I'm going to find this distance. Right, so it's going to be magnitude. What do they do? R minus R prime. Okay, so this is how you deal with the charge that is not centered on your coordinate system. Why do we want to deal with? Because in real life we don't have only one charge to worry about. We might have multiple charges. We might have multiple charges. So I have 4 charges, 5 charges, and I want to find the potential field around those 5 charges. So I need to know the location of each of those 5 charges. So I need to know R1 prime, R2 prime, R3 prime, R4 prime, R5 prime. I need to know the location of each of those 5 charges, and then I'm calculating the field at the general point P, and the R represents the position vector to that point where I'm calculating the scalar field. So the scalar field is going to be just the sum. It's going to be Q1. So each charge has its own charge. Each point charge has its own quantity for charge. It's going to be Q1 over 4 pi epsilon naught R minus R1 plus Q2 over 4 pi epsilon naught R minus R2 hat prime. Remember the prime. It's always convention to use prime when you're dealing with sources, right? Dot, dot, dot. So if you have, like, let's say n charges distributed in space, n charges located at R1 prime, R2 prime, all the way to Rn prime. So those are the locations of those n charges, and you're finding V at P, then V at P is going to be the sum of K from 1 to n of Qk over 4 pi epsilon naught magnitude R minus Rk prime. It's a matter of superposition, summing everything up. And of course, where this is heading, the same thing we did with the Coulomb's law, is if you have now charge distributions, you can divvy them up into an infinite number of point charges, and you can integrate over the charge distributions to get the voltage field. Okay. So let's go back to interpreting this physically. Okay. So VP2 minus VP1. So this is the expression that naturally arises from the nature of the gradient, mathematical nature of the gradient. So let's go deeper into its physical interpretation. We said it has something to do with energy per unit charge. Let me write it down again. So VP2 minus VP1 equals minus the integral from P1 to P2, line integral, E dot dl. Okay. Now for a point charge, what does that mean? For a point charge, Q. Okay. The way we interpret this, let's say P1 is at infinity. P1 approaches infinity. P1 is at infinite distance, right? And we said at an infinite distance, so if P1 approaches infinity, VP1 is 0. By convention, VP1 is 0. I selected my V. I have choice in selecting my V. I can add a constant. But I selected my V such that VP1 is 0. So this tells me that P2 is my endpoint. So P1 is at infinity. I move a charge, some charge Q, capital, from infinity to some point P2. So VP2 is minus integral from infinity to P2 E dot dl. What does this represent? E. What does E represent? E is force per unit charge. So if I'm using a charge Q, right? Let's say I multiply both sides by Q. Q times E is force. So this is the electrostatic force. So I'm moving a charge here against the electrostatic force, right? So the system is getting, it's like moving a boulder uphill. You're working against gravity. So you're adding potential energy to the system. So I'm moving a charge from infinity, the bottom of the well, closer to the charge, right? So you're gaining potential energy. You're working against the field. And this is force times distance. This is work. This is work. So you're pumping energy. What you're doing here, and by the way, the subtle thing here is that moving charges gives me dynamics. So it doesn't work anymore. You have to imagine that you're moving the charge really slowly so that things are almost static, right? So you're moving the charge really slowly such that there is no current, right? So everything remains electrostatic. But if you move the charge really slowly, the system is gaining energy, right? So V really is a measure of how much energy you need to move the charge from infinity to P2. How much energy, V is a representation of how much energy per unit charge. Like if I had 1 Coulomb, how much energy would I need to move it from infinity to P2? That's the voltage at P2, right? So it's the energy per unit charge needed to move a charge from infinity to a certain point. That's what the physical interpretation of the scalar field, potential field is. And this works if you have a charge distribution or a bunch of point charges, it's the same. If you have some outlier charge at infinity, how much more potential energy you will add to the system by moving this charge closer. So let's say I move this charge from infinity to point P. V at P represents the energy per unit charge that is needed to move this outside charge to this point. This is the physical interpretation of the potential field. It represents, it's a quantification at every point of space of how much energy you need to move an outside charge, outside meaning an infinite distance away, into that point. And when you do that, you increase the energy of the system because now you have more stuff happening in the system, more charges, larger fields, right? So it takes energy to grow the field. As we will discover later, the field itself has energy, right? And this is something we will discuss. So I guess let me do an example. 3-point charge. Okay, let's do example 4.7. Oops. Three-point charges are arranged as shown in this figure. So I guess it's just two-dimensional, X, Y. They're arranged on a plane. Okay. And then I have charge A, which is minus 2Q, which is a distance A. And then a distance A2 is minus 3Q. This is charge B. And then I have charge Q, which is a distance B. And then I need to find at a certain point, so this is point X, Y, Z is 0. This is a point on the plane. I need to find what is the field there, I guess. That's the problem. Okay, so yeah, so all I need to do now is find the distances, right? Because the distances figure prominently in the equation for the potential, right? So I have RA, and I have RB. Then I have, this is charge C, I have RC. And RA is from the Pythagoras theorem, right? So RA is going to be so it's going to be X minus A. It's going to be X plus A. So RA is going to be X plus A squared plus Y squared. RB, this distance is going to be X minus A squared plus Y squared. It's all application of Pythagoras theorem. And then RC is going to be X minus, this point is 0B, right? It's going to be X minus 0. It's going to be X squared plus Y minus B squared. And then we know that V for every point charge is going to be Q, whatever the charge is, over 4 pi epsilon naught R. So V at point P is just going to be the sum, right? So it's going to be, so there's going to be 1 over 4 pi epsilon naught. And then there's going to be Q. I'll take the Q out. And then charge A is going to be -2. So it's going to be -2 over RA, which is square root X plus A squared plus Y squared. And then B is -3. So it's going to be plus -3 over RB, X minus A squared plus Y squared. And then C is going to be Q, just Q. So it's going to be 1 over RC, which is X squared plus Y minus B squared. This is it. This would be the voltage at any point. And this is in units volt. Remember, volt is energy per unit charge. So it has units of Newton per meter over Coulomb. Right? And Coulomb is amps per second. If you want to go back to the fundamental units, the fundamental unit is actually amps. So this is how we write it in the fundamental units. Newton even is not a fundamental unit. It's not a fundamental SI unit. Newton is what? Newton is force. Force is mass times acceleration. So it's kilogram meter over second per second, second squared. So Newton actually is kilogram times meter, meter squared over second squared, amp times second cubed. So this is really fundamental SI units. This is what the volt is. Remember, in SI units, the fundamental units are the amp, kilogram, meter, second. That's it. Anything other than that is the derivative unit, which is fine. You can have derivative units, like N is a derivative unit, V is a derivative unit, Coulomb is a derivative unit. Okay, just to segue back into units, just as a reminder. Okay, so charge distributions. This is simple. This is even simpler than Coulomb's law. So charge distributions. Potential due to charge distributions. So the idea is that now in the similar way where we dealt with the linear line charge distributions. So I have here rho L. Surface charge distributions, rho S. Rho L is Coulomb per meter, rho S is Coulomb per meter squared, and then volume. This is rho V in units of Coulomb per meter cubed. We can calculate for those, let's say in space, we have those charge distributions. We can always calculate at a point P, this is in space. I mean, a coordinate system is not necessary for space. It's a human invention, but it's necessary for us to do calculations. So at any point P, the summation that we have to do to apply superposition turns into integration, essentially. That's what it turns into. So for a line charge, what we have to worry about two things. We have to worry about, let me see. So we have to integrate on the line. So at every segment in the line, there is R prime. And R prime here varies depending on where you are on the line, right? So there is a line integral here. So we have to say V at R. So we want to find V. R is the position of the point. Position vector of the point in space. This is a point in space from the origin. R prime is the position vector from the source to the point. And R prime varies depending where you are on the source. So V at R is the sum over L prime. L prime represents integrating over the line. So you're moving along the line, right? DL prime, right? So this is not a vector integral. This is not a line integral. This is essentially parameterizing the line by some variable L and varying L prime by variable L prime and then varying L prime so that you move along with the whole line, right? So we have DL prime here and there is the charge. The charge is rho L DL prime. That gives me the charge for every small segment. So this is DL prime. So this is the charge over 4 pi epsilon naught. So I take out the 4 pi epsilon naught. And then R magnitude. R magnitude in this case is the magnitude of this vector, which is magnitude R minus R prime. This is it, volt. Now, what is constant? Rho L could be constant. You could have a uniform charge distribution. In this case, you can take rho L out, but notice I did not take rho L out. The reason is that rho L could be variable. The charge distribution could vary along the line. It could be more condensed somewhere and more. So it could be a function of where you are on the line. R is constant because R is the field at a constant point in space that you're calculating. So R is constant. R prime, however, varies with DL prime. So it has to remain under the integral. It's always important to be wary of what needs to remain under the integral and what you can take out. Now for the surface, it's the same deal. VR is going to be 1 over 4 pi epsilon. But now I have I integrate. I have two parameters. I have S prime, right? So I integrate over the surface. I parameterize the surface somehow. I have to integrate over the whole surface. So it's going to be integral over S prime of what is the charge? The charge is rho S, and rho S is going to depend on where you are, of course. So this is point P, this is R, this is R hat, R prime, right? So rho S ds prime is going to give me the charge over R minus R prime magnitude V. And then finally, the same thing for the volume. I need to parameterize the volume. I can use a variable V prime to represent where we are in the volume. Right? It's essentially 3 coordinates. It's going to be V1 prime, V2 prime, V3 prime, X1 prime, X2 prime, X3 Y prime, Z prime, or R capital prime, theta prime, Phi prime, whatever it is. It's a parameterization of the volume. And VR in this case for a volume is going to be the same thing, but now it's going to be a volume integral. Meaning when you do this integral, you have to split it 3 times, do it 3 times. Rho V dV prime over R minus R prime magnitude V. Okay. And the idea is that hopefully this will be simpler to do than applying Coulomb's law, because everything in this case is a scalar. It's not a vector. I guess we could do, let me see. We could do an example that we did, I think, with, we can do an example that we did previously using Coulomb's law, which is the line segment. I think we did an infinite line segment, and then we did do, let me see where it is. Maybe here. So we did, yeah, we do this example. So this has a line segment with length L, and we try to find what the field is, and the field turned out to be this. We want to do this in terms of the voltage. Oh, what happened? Oh, it's kind of. So let's redo this example, but using the scalar field, the potential field, instead of the electrical fields. It's the same kind of problem. So we have Cartesian system. We have a line segment, a rod essentially, with Z prime going to L over 2, Z prime starting at minus L over 2. So the whole thing has a length of L. And we're using a cylindrical system. So point P away. So we're trying to find the field at the center of the rod, right? A distance R away. So point P has coordinates R, phi, 0, Z is 0, right? And this would be phi, I guess. And then we have dl prime here, which equals z hat dz prime. That's what it is essentially. And then, yeah. And then, yeah, wherever we are here, this will have coordinates z prime. So z prime is the coordinate of the rod. It does not vary. There is no theta prime or phi prime because we're only moving along the z-axis. So we're only integrating across z. So the question has two parts. It says, can we calculate the potential at the general point in space? So let's say I have a point P, R, phi z. This is any point in space, right? So this kind of thing, it is going to have I guess he's not using R prime, but it should be R prime. So this is R prime. And then this distance is Z minus Z prime. Okay. And then phi could be phi could be anything, okay? So what is the distance between what is this distance between any segment of the line and the general point in space? So that's easy. So R prime magnitude. So you're going to need this distance to apply the potential Pythagoras theorem, right? What is this distance here? This distance is R. What is this distance? Z minus Z prime. So it's going to be R squared, R from the cylindrical coordinates. I think it's confusing. Why does he use small r? Because it implies that small r is for the cylindrical. Let me use capital R here and use prime. Okay. So that's a little bit confusing in the book. Okay. So R capital prime magnitude is just R squared plus Z minus Z prime squared. Right? So this is the magnitude. This is going to be in the denominator. What is dV? What is the voltage due to this small segment then? Is going to be rho L dz prime. Dz prime is the length of that small segment. So this gives me the charge over 4 pi epsilon naught. The magnitude R, the distance from that segment to the general point. So that's going to be square root R squared plus Z minus Z prime squared volt. And now the full voltage in general at R phi Z is just going to now be rho L is constant in this problem. So I can take it outside the integral. Rho L over 4 pi epsilon naught. And now I integrate from minus L over 2 to L over 2 dz prime over R squared plus Z minus Z prime squared. So I'm integrating with respect to Z prime. So that would be the general voltage. And you can integrate this. If you go back to your table and you integrate table or use software, you will find that the logarithm will show up here. So this is going to be rho L over 4 pi epsilon naught len something like 2 r squared plus z minus L over 2. Yeah, this you can find using MATLAB or Mathematica or using an integration table. I mean, this is not an integration course. But the expression can be calculated, and it's going to look something like this. Okay, but the point is that you reduce the problem to doing this scalar integral. Of course, how do you get the field at the center of the rod? You let z equal 0. Let z equal 0, and that gives you the field at the center of the rod. That's one reason I like to give exams for this course take home, because I don't want people to worry about calculating an integral within the confines of, I don't know, 60 minutes or something like that. Of course, if you have, once you calculate the potential, let's say I have V, how do I find E? E is now simply minus grad V. And what is grad phi for cylindrical coordinates? So for cylindrical coordinates, we did that, and we found out that grad V is minus delta V over delta R, R hat, plus 1 over R, delta V over delta phi, phi hat, plus delta V over delta Z, Z hat. So once you calculate V, just do those direct differentiation to find E. You can always directly find E from V. And V is easier to calculate because, again, it's a scalar field. Okay, I'm gonna stop here. Any questions? All right, so after this, Alexia is gonna kind of go through some problems. So if you want to join there, you can after this lecture around, I think it starts at 10. I'm gonna see you Friday.